All right. That was an intentional all right, by the way. We're going to start talking about substitution in this section because we have all these rules for finding derivatives, and antiderivatives are harder, okay? We've mentioned that earlier that you can basically take the derivative of anything. We cannot basically take the antiderivative of anything, and it's usually less straightforward. Derivative is just follow the rule, do the thing. Antiderivative is a lot more of like puzzles, like problem solving. Like, well, let's try this. Oh, that didn't work. Oh, let's try this. Oh, that didn't work. Because we're trying to go backwards. Antiderivatives is really all about going backwards. And here it's usually easier to go forwards. The advantage to antiderivatives is that you can check your work with Calc 1 and you can know whether your antiderivative is correct or not. Whereas for derivatives, you could really only check it with technology. But here we can check everything by hand. So there's some advantage to that. So what we're going to do is start by taking a trip down memory lane. We have something called the chain rule for derivatives. Pretend that's a D in the denominator, okay? That if I want to take the derivative of a function inside of a function, maybe this is e to the x squared, maybe this is a natural log of 3x, but some function inside of some other function, the chain rule says that we take the derivative of the outside function, we leave the inside function alone, and then multiply by the derivative of the inside function. So, as you might expect, we have this whole table with derivatives on the left and integrals on the right. And every derivative formula has an integral formula. Well, today we're going to talk about what does the integral formula look like for the chain rule? How can we undo the chain rule? And that is what we're doing. Later on, we'll undo the product rule. We will never really undo the quotient rule. And then I don't think we do anything that corresponds to logarithmic differentiation. But substitutions are nice and very, very powerful tools. And we'll introduce some of them and also show about some ways to use substitution that you might not think. So we don't call it chain rule. This method, this analog to the chain rule is called substitution. I'm getting ahead of myself a little bit. Let's look at an example of this. What if I want to take the derivative of e to the x squared that I mentioned earlier? Well, the outside function is e to the x, and the derivative of that is itself. So we took the derivative of e to the x, which is e to the x. We left the inside alone. It's still just an x squared. We multiplied by the derivative of that inside, 2x. And there was another form of the chain rule with like u's in it. That's also very useful and will actually make a lot of sense in this section as well, because a lot of times for substitutions, we do use u's. So again, what we know is that antiderivatives just undo derivatives. So because we know that the derivative of e to the x squared is that tells us immediately that the antiderivative of that is e to the x squared plus any constant. And this is what we're doing. We're formalizing this process. Saying, okay, how can we go from here to here without just, starting with this circled value? That is what we are doing. That is what substitution is all about. So let's introduce the method and then see it in action. So we got some assumptions here that aren't going to come too much into play in this class probably, but they can come into play later. And everything's tilted, so I'm writing like a little tilted up. I don't know why my workspace is so tilted today, but I don't know. So we're going to start by letting u be g of x. We always think of u as our inside function, f of g. Or g is that inside one. So u is going to be that inside function. And here we're going to say, we're going to require that g prime is continuous. And we're going to require that f, our outside function, is also continuous not everywhere, but it has to be continuous on the range of G. We're also going to say that f prime is f of x. So in other words, capital F is an antiderivative of lowercase f. We'll always be using this notation in this class. Not always is a strong word. Usually when we see a capital F, we'll mean it as an antiderivative of little f. And same with like G and H and stuff, usually. And again, I want to make a quick comment before we get to the punchline of this. I know, a little cliffhanger for you guys. Why do we need to assume that f is continuous on the range of G? Well, because look at what's happening. We're looking at this function. So G, the output of G, the range of G, is going to be the input of f. So f has to be continuous on that input, and that input is the output of G, which sounds kind of weird, but you can think about it. You can think about it that way. So here's what we have. Here's our substitution rule. It says if I want to integrate some function inside of a function, if I'm trying to find the antiderivative of some function inside of a function, well then, if I have the derivative of the inside, if this g prime of x is there, or if we can get it there, sometimes we have to put it there. If that's there, then we can substitute with u being g of x to get this to become actually just f of u, now with our variable of integration equal to u. And I'm going to show when we actually do an example where this substitution comes from, because this part is straightforward. U is just the same thing as g of x. But this part is usually a little less easy to see, and we'll show that in the example. And what it has to do, you know, I'll go right now. We're not going to wait. I'll show you why right now. So an idea, right, is if u equals g of x, what happens if we take the derivative of both sides with respect to x? We get du dx equals g prime of x. Now, this is not a fraction. We write it like a fraction, and a lot of times it behaves like a fraction, but it's not technically a fraction. However, if we use basically some measure theory, which is way outside the scope of this course, we get that this is also true. And you can kind of think about it as multiplying both sides by dx. That's not technically what's happening, but it's very closely related. So that's why we get this, just becomes our du. So that's the intuition behind this substitution rule. And then once we know that, well, we know the antiderivative of f. So the antiderivative of f is just capital F, still evaluated at u, plus some constant. And then again, we know that u is f of g of x. So we can get everything back in terms of x at the end, which is going to be important to remember. If the original problem gives you a variable, your final answer should be in terms of that variable. Substitutions are all well and great, but make sure to return to where you started. So this is just our method that we'll be working on for the next two videos. The next two videos are just more examples of this, of how to evaluate certain integrals if the derivative of an inside function, we want to use, basically undo the chain rule. And that's what we're doing. So we'll have one kind of, hey, here's how it works. And then most of the examples will be in the next two videos. So example 1, evaluate the integral, the antiderivative of x squared minus 3 cubed times 2x dx. Now you don't need the parentheses this way, and in fact usually you're not going to see them, so I'm not going to write them that way even though I initially planned on it. So this is an example of undoing the chain rule. This is an example where substitution is useful. This is what we think of as our inside function. We do not know that this is G. Sorry, we don't know this is G. We don't know this is U. But we notice a relationship between these two red things. That if we guessed that this was U, well then look, that's the derivative. And that's what we're looking for when we're using substitution. Trying to choose a good U, because with practice it becomes easier, but it is not obvious at any stage. Well, obvious is subjective, but it's not guaranteed at any stage. But we want to choose our U so that there's a U prime on the outside. So here, we're going to start by saying, I don't know how to do this integral. We can't evaluate the integral of each one individually because products of derivatives, you can't take the derivatives individually either. So same with integrals. If you have two functions multiplied, you can't just integrate them individually. That's only for constants. So we can't just integrate these individually. We're going to have to use a substitution method. And if you're ever curious about, can I do this? Well, write your guess and check by taking the derivative. But here, this is what I think. I say, okay, usually our inside function is going to be our u, or our g of x. And then hopefully its derivative is either on the outside, or we can get the derivative on the outside. So let's go off to the side and say, all right, if we let u be this inside function, as a guess, it's a good guess. But as a guess, if we let u be this inside function, what's the derivative of u? Well, the derivative of u with respect to x is 2x. That's great. Because if we think, because that also tells us by the property on the first page, it also tells us that du is 2x dx. Again, you can think about this as multiplying both sides by dx. Not technically what's happening, but that's how you can remember it. Because this is nice. Because that means that this guy, 2x dx, perfect. 2x dx is exactly our du. So this integral just becomes the integral of u cubed times du. And remember, the variable doesn't matter. As long as this and this have the same variable, we can integrate no problem. So usually we call these u substitutions because u is most common, but you can substitute with any variable. And sometimes you're going to have to make multiple u substitutions, and then we'll use like w substitutions or maybe a v substitution. You got to be careful about v because u and v kind of look really similar and you don't want to confuse anybody, least of all yourself. So now we can integrate with the power rule. Add a power and divide by that power. But we're not done. If the problem gives us x's, let's answer with x's. So what is u? Actually, yeah, I will write this down. What is u? Well, u is x cubed minus 3. So this becomes x squared minus 3 to the 4th power plus c as our final answer. And I cannot recommend this enough. On homework problems, on quiz problems, on exam problems, when you're, doing your nightly for dessert, you eat a nice dinner, and then for dessert you let yourself do some calculus problems, maybe save the really good stuff for after you eat your meal. Make sure to check your work, because antiderivatives undo derivatives, so we should be able to go back. If I take the derivative of my final answer, the derivative of 1/4 times x squared minus 3, this is also good because it helps you practice your Calc 1, which we'll be using. Well, we're going to use the power rule, bring down the power. Okay, those cancel. Leave the inside the same. We have to use the chain rule. Subtract the power. Multiply by the derivative of the inside. The derivative of x squared minus 3 is just 2x. And the derivative of c is 0. So now my question is this where we started? Sorry. Yeah, that's the same thing. Great. Can do a happy check mark face. And that's how we can know that our answer is correct. And that's it for this video. Next 2 videos, nothing new, just some different ways that this can appear and some more practice. Good luck, and let me know if you have any questions.